Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So previously in part number 2, we already discussed about an ideal vapor compression refrigeration cycle. So now for part number 3, we will discuss about an actual vapor compression refrigeration cycle. Actual vapor compression refrigeration cycle. So for an ideal vapor compression refrigeration cycle, we can refer to this TS diagram. So this TS diagram is the TS diagram for ideal vapor compression refrigeration cycle that we have learned in part number 2. So in terms of characteristic of the TS diagram for the ideal vapor compression refrigeration cycle, so we have 4 states involved and also 4 processes involved. First process involved with state number 1 to state number 2, which is the isentropic compression process in the compressor, where in terms of phase, state number 1 will be at saturated vapor. So we have isentropic process where S2 equal to S1, and the state or the phase for state number 2 will be in superheated vapor. And then the second process is the heat rejection process at constant pressure, where P2 equal to P3. So in terms of phase, state 2 at the inlet of the condenser is superheated vapor, and at the outlet of the condenser in terms of phase will be at saturated liquid. Okay, so the third process involves throttling process in the expansion valve, where at the inlet of the expansion valve, state number 3 in terms of phase is saturated liquid, and outlet of the expansion valve will be at saturated mixture. And the main criteria during this process is H3 equal to H4. So the last process involved is heat absorption process in the evaporator at constant pressure, where P4 equal to P1. Okay, so in terms of phase, state number 1 at the inlet, state number 4 at the inlet of the evaporator will be at saturated mixture. At the outlet of the evaporator, state number 1 is at saturated vapor. Okay, and during the process, the pressure is constant. So when we discuss or when we consider the actual cycle, so we need to consider irreversibilities such as what we call heat losses, heat gain, and so on, friction and so on in the connecting line and also in the device. We also need to consider the heat transfer process in and out from the system, in the device, in the connecting line and so on, and also due to the fluid friction inside the piping line, so we will have pressure drop. So if we look at the schematic diagram, instead of previously in ideal vapor compression refrigeration cycle, in the schematic diagram we only consider 4 states. Now because we consider irreversibilities in the device and also in the connecting line, so as an example, we will use instead of 4 states, we will use 8 states as shown in the schematic diagram. Okay, from state number 1 until state number 8. Okay, so if we draw the TS diagram for the actual vapor compression of the cycle, so we will have we can describe the process as shown in the second TS diagram for the actual vapor compression refrigeration cycle as shown in the TS diagram. So we have state number 1 until state number 8. Okay, so for each state we will have different different phase we compare to the ideal vapor compression. Okay, so if you compare to the ideal vapor compression refrigeration cycle in terms of TS diagram, state number 1 at the inlet of the compressor will be at superheated vapor, where if it, as a comparison, if you look at the TS diagram for the ideal one, the inlet state number 1, the inlet condition or the inlet phase for the compressor will be at saturated vapor. Similarly to the condition or the phase at the outlet of the condenser. So for the actual one, the phase for the outlet of the condenser will be at subcooled liquid or at the compressed liquid region. However, in the ideal vapor compression refrigeration cycle, the state or the phase at the outlet of the condenser will be at saturated liquid. So if you look at the evaporator, so preheating process will occur where refrigerant completely vaporize due to few factor. Okay, so in the actual one, at the outlet of the evaporator, especially state number 8, the phase of the refrigerant will be at superheated vapor. So the reason, because we have heat gain at the connecting line. Okay, at the connecting line between the evaporator and also the compressor, and also due to the pressure drop in the evaporator, where now the heat absorption process in the evaporator is not in constant, is not at the constant pressure, where P7 now not equal to P8. Due to this pressure drop, the refrigerant specific volume at the inlet of the compressor will increase. When the volume increase, okay, especially for state number 1, we need to provide more W into the compressor in order to compress the increase of volume of the refrigerant, and more power input required in the compressor. Okay, so we need to supply more W in. So at the compressor, during the compression process, at the inlet, especially state number 1, the phase of the refrigerant will be at superheated vapor. Due to the friction, because we consider friction effect in the connecting line, the entropy also will increase due to the increase of temperature of the refrigerant. And the heat transfer process, for example, heat transfer from the surrounding to the connecting line, also will increase the entropy value. And this entropy value, due to the heat transfer, actually depend on the heat direction. So if the heat transfer from surrounding to the refrigerant, the entropy value will increase. But if heat transfer from the refrigerant to the surrounding, the entropy value will decrease. So that's why the value of entropy based on the heat transfer actually depend on the direction of the heat transfer. Okay, now at the condenser, in the condenser also we have pressure drop, where now during the heat rejection process, the pressure is not constant, because this now we consider the actual cycle. So P3 is not equal to P4. So in the connecting line also we will have pressure drop. Okay, so for example, point number 4 and also point number 5. So pressure at point number 4 is not equal to the pressure at point number 5. So that's the meaning of the pressure drop in the connecting line for the condenser. The outlet of the condenser refer to state number 4. Actually, if we based on the ideal vapor compression refrigeration cycle, state number 4 will be at saturated liquid. However, in the actual process, actually it is hard to maintain the condition of state number 4 at the outlet of the condenser at saturated liquid. Okay, so thus in actual condition, state number 4, or the condition of at the outlet of the condenser, will be at subcooled liquid region before the refrigerant entering the throttling device. Okay, so that's the criteria or the characteristic for the actual vapor compression refrigeration cycle. Okay, subcooled liquid region for state number 4. Okay, now about the analysis for the actual vapor compression refrigeration cycle. So this is the schematic diagram for the actual vapor compression refrigeration cycle, and the second figure shows the TS diagram for the actual vapor compression refrigeration cycle. So now you have to differentiate in terms of the formula for the actual vapor compression refrigeration cycle and also the ideal vapor compression refrigeration cycle. So in order to determine the formula in terms of QL, QH, W in, so you need to refer both schematic diagram and also the TS diagram. Okay, And your analysis, you need to implement the energy balance equation for specific device in order to determine the specific formula for QH, QL, W in performance and so on. So for in terms of heat transfer, so the formula for QL and also QH, QL equal to H8 minus H7. So in terms of state, you need to find the closest point of the inlet and also of the outlet for each for each device. For example, if you want to determine QH formula, so you need to refer the closest point or the closest state at the inlet and also at the outlet for the condenser. So that's why we have, okay, for the condenser, QH equal to H3 minus H4, because the closest state at the inlet and also at the outlet of the condenser will be state number 3 and also state number 4. Okay, now for work formula, where we have only one work, which is referred to work W in, the work that required by the compressor. So W net in equal to H2A minus H1. Okay, so the general formula is H2 minus H1, but now because we consider actual vapor compression refrigeration cycle, so we need to consider H2A, where W net in equal to H2A minus H1. So clearly can be seen, we can see clearly the formula by referring to the TS diagram. And then for the throttling process, if you look at the expansion valve for the throttling process, so the state that involved at the inlet and also the outlet of the expansion valve are the state number 5 and also state number 6. And the main criteria for the throttling process for the actual vapor compression refrigeration cycle, for this case, H5 will be equal to H6. And the last formula is involved with the performance, where the value of COPR will be equal to QL divided by W net in, COPHP equal to QH divided by W net in, and we have another performance formula when involved with actual vapor compression refrigeration cycle, which is the compression isentropic efficiency. The compression isentropic efficiency, which is referred to the isentropic efficiency for the compressor. So the formula will be mu C equal to W in S, which is referred to the ideal W in, divided by W in A, which is referred to W in actual. Okay, because normally W in actual will be greater than W in ideal due to the irreversibility factor that occur during the compression process. So if you base on the enthalpy value, so mu C isentropic efficiency for the compressor will be H2S minus H1 divided by H2A minus H1. Okay, so in order to determine all the parameters QL, QH, W in, COPR, and also mu C, so you need to have the value of enthalpy for each stage. Example 5.2. Refrigerant 134A enters the compressor of a refrigerator as superheated vapor at 0.14 MPa and negative 10 degrees Celsius at a rate of 0.06 kg per second, and leave at 0.8 MPa and 50 degrees Celsius. The refrigerant is cooled in the condenser to 26 degrees Celsius and 0.72 MPa and is throttled to 0.15 MPa. Disregarding any heat transfer and also pressure drop in the connecting line between the component. Determine A. The rate of heat removal from the refrigerated space and the power input to the compressor. B. The isentropic efficiency of the compressor. And C. The coefficient of performance of the refrigerator. So for this example, the question gives you in terms of data for four states where we have pressure drop during heat rejection process and also pressure drop during heat absorption process in the problem. Okay, so this question involves the actual vapor compression refrigeration cycle. Okay, solution for example 5.2. So what you have to do first draw the spectral diagram and put whatever data given in the question. So from the data given in the question, you have 4 states involved. State number 1, in terms of pressure and also temperature given. Pressure at state number 1, 0.14 megapascal, and temperature at negative 10 degrees Celsius. State number 2, after the compression process, the pressure is at 0.8 megapascal. The temperature is 50 degrees Celsius. After heat rejection process in the condenser, the pressure dropped to 0.72 megapascal with temperature of 26 degrees Celsius. So after the throttling process, the pressure dropped to 0.15 megapascal. So these are the data given in the question. And also the question also gives you the value of mass flow rate, because later on you need to calculate the rate of Q, the rate of work, and so on, where m dot equal to 0.06 kilogram per second. So at this point, you cannot draw the exact TS diagram yet, but however, you will get a few information for the TS diagram. So based on the data given, you will have 4 constant pressure line. We have a lower pressure line, lower constant pressure line for the evaporator, where we have 2 constant pressure line, 0.15 megapascal and also 0.14 megapascal. Upper part of the constant pressure line consists of 0.72 megapascal and also 0.8 megapascal. And we have mass flow rate equal to 0.06 kilogram per second. So we have QL, QH. State number 1, we still not know about the exact phase of state number 1, so we need to check. And if after we get the state number 1 in terms of phase, so we'll get the value. We just draw the vertical line, intersect with 0.8 megapascal. We'll get the point for the state number 2s for the isentropic process. And then we know that for the actual one, the value of W in is greater than the value of W in for the ideal one. So we will have 0.2a slightly higher than 0.2s. So we will have W in during the compression process. State number 3, also still we do not know yet the exact phase for state number 3, so we need to check by using saturated R134A table. And state number 4, also we do not know the what I call the exact value in terms of H4, but we know the phase will be in saturated mixture region, and the pressure will be at 0.15 megapascal. So these are the data that we can obtain from the TS diagram, but the TS diagram is not complete yet. So after we determine all the value of enthalpy and so on, so we can draw the complete TS diagram for this question. So after that, we need to determine the value of QL dot W in dot mu C, the isentropic efficiency for the compressor, and the last one we need to determine the performance of the refrigerator, COPR. Okay, first step, in order to solve the example 5.2, so we need to determine all the important value, especially the value of H enthalpy for the cycle for all states. So this is the schematic diagram for the problem. In terms of data given, so we have P1 equal to 0.14 megapascal, T1 equal to negative 10 degrees Celsius, P2 equal to 0.8 megapascal, T2 equal to 50 degrees Celsius, P3 equal to 0.72 megapascal, T3 equal to 26 degrees Celsius. For state number 4, we have P4 equal to 0.15 megapascal. And also the data, the question also give you the value of mass flow rate, where m dot equal to 0.06 kilogram per second. For state number 1 will involve isentropic process from state number 1 to state number 2s. So as I mentioned before, for the table of R134A thermodynamic table, at least you need to have 2 information or 2 data before you can use the table. So now for state number 1, we already have 2 data. First, P1 equal to 0.14 megapascal. The second one, T1 equal to negative 10 degrees Celsius. But now, because we do not know the exact phase for state number 1, So we need to check first by using saturated R134A table based on pressure. Okay, so based on the table, at pressure of 0.14 megapascal, we can determine T saturated, where the value of T saturated for state number 1 will be T saturated at 0.14 megapascal equal to negative 18.8 degrees Celsius. Compare the value of T saturated with the value of T1. So T1 will be greater than T saturated at 0.14 megapascal. So the phase for state number 1 will be superheated vapor. So now in order to determine the value of H1, so we need to refer to the superheated vapor R134A table. Okay, kalau refer to the superheated refrigerant 134A table, so at pressure 0.14 megapascal and temperature negative 10 degrees Celsius. So from the table we can determine the value of H1, where H1 equal to 246.36 kJ per kg. And also we can determine the value of S1, because later on we will use this formula for the isentropic compression process, where S1 equal to 0.9606 kJ per kg Kelvin. Okay, done state number 1. State number 2, for state number 2 we have two condition. We have state number 2 for ideal condition and also state number 2 for the actual one. First we determine for the ideal state, where the state refer to state 2s, and this state refer to will involve with the isentropic process. So P2S will be equal to P2 equal to 0.8 megapascal, and S2S equal to S1 due to the isentropic process equal to 0.9606 kJ per kg Kelvin. So for state number 2, as we already have two information or two data, so we can determine call the value of H2S. Okay, so the phase automatically we can know the phase of this refrigerant after the compression process, because initially at the inlet of the compressor the phase already superheated. So for sure the condition in terms of phase for the compressor outlet will be superheated vapor. But if you want to determine, still want to check the phase, you can use the same method in order to determine the phase by using the saturated refrigerant R134A table, as I mentioned in state number 1. Okay, let's say we already confirmed the phase is superheated vapor for state 2s. So refer to the superheated refrigerant 134A at 0.8 megapascal. So now you need to refer to the value of entropy that you obtain for S2S, where the value of S2S equals to 0.9606 kJ per kg Kelvin. So you need to find out the value of S2S in the table, and the value is in between 0.9374 and also 0.9802. So you need to make interpolation between the entropy value and also the enthalpy value. So from the interpolation, so you will get the value of H2S equal to 280.72 kJ per kg. Okay, now we continue with the second part of state number 2. So we have state number 2 for the actual state 2A. So the pressure for state 2A also same as the pressure for state 2S, where P2A equal to P2S equal to P2 equal to 0.8 megapascal. And we know that the temperature given in the question refer to the actual, the temperature given in the question refer to the actual temperature at state 2A. T2A equal to T2 equal to 50 degrees Celsius. So now we have two information. But now, because for state 2S, the phase already superheated, so the state for state 2A also in superheated vapor region. So now we just let's say still you want to check the phase for state number 2A, so you can use saturated refrigerant 134A based on pressure table. So at pressure of 0.8 megapascal, determine T saturated. So T saturated at 0.8 megapascal equal to 31.33 degrees Celsius. Compare with T2A value. So you get T2A is greater than T saturated at 0.8 megapascal. Okay, so the phase confirm superheated vapor. So now refer to the superheated vapor table for refrigerant 134A at pressure of 0.8 megapascal and the temperature 50 degrees Celsius. Directly from the table, you can determine the value of H. So this value of H refer to the value of H2A. So H2A equal to 286.69 kilojoule per kg. Okay. Okay. Now, okay. So we already done for state 2A and also 2S. So now for state number 3. So the data given P3 equal to 0.72 megapascal, T3 equal to 26 degrees Celsius. So we have two data, but still we don't know the exact phase for this state number 3. So we need to check by using saturated refrigerant 134A table based on pressure table. So the pressure is 0.72 megapascal, so we cannot get directly from the table. So you need to make interpolation for the value of 0.72 megapascal. Okay, make interpolation between the pressure value and also the saturated temperature. So from the table of saturated refrigerant R134A table, so you can determine the value of T saturated at 0.72 megapascal, which is equal to 27.64 degrees Celsius. Compare with the temperature given. So T3 is less than T saturated at 0.72 megapascal, which means the phase is subcooled liquid or compressed liquid. However, the data is not available for subcooled liquid of the refrigerant R134A. Thus, we need to make assumptions. So we assume the closest condition. We assume state number 3 as the saturated liquid at 26 degrees Celsius. Okay, so we need to base on temperature to reduce the error during the calculation. Okay, so now we need to refer to saturated R134A table based on temperature table because we make assumption. So at 26 degrees Celsius, so we can determine the value of H3, where H3, because we assume as saturated liquid, H3 equal to HF at 26 degrees Celsius. So H3 equal to HF at 26 degrees Celsius equal to 85.75 kJ per kg. Okay, so the last state for this cycle is state number 4 that involves with throttling process. So we have, in terms of data, we have P4 equal to 0.14, P4 equal to 0.15 megapascal, and we know that the phase for state number 4 will be in saturated mixture region. However, for state number 4, no need to determine the value of enthalpy through the table because we know that during the throttling process, the value of H4 will be equal to H3. So we just take the value of H3 equal to H4. So H4 equal to H3 equal to 85.75 kJ per kg. So now we already have all the important value of enthalpy for all states. So now we answer the question for the example 5.2, where the question asks you for question A, the rate of heat removal from the refrigerated space, which is referred to the value of QL dot, and also the power input to the compressor, which is referred to W in dot or W net in dot. So refer to the rate of heat removal formula where QL dot equal to M dot multiplied by H1 minus H4. So substitute all the values, so we'll get QL dot equal to 9.6366 kilowatt. For the power input, W in dot or W net in dot equal to M dot multiplied by H2A minus H1, because now we need to consider the value of actual enthalpy for actual state. So now we need to consider H2A. So substitute the value. So the value in equal to 0.06 multiplied by 286.69 minus 246.36 equal to 2.4198 kilowatt. Okay, we already answered the question number A. Question B. So you need to determine the isentropic efficiency of the compressor. So refer to the isentropic efficiency for the compressor and also the TS diagram. So we have mu C equal to H2S minus H1 divided by H2A minus H1. So we already have the value of H1, H2S and also H2A. Just substitute into the equation. So we'll get mu C, the isentropic efficiency for the compressor will be equal to 0.8519 or 85.19%. And the last one, you need to determine the value of COPR. So we have the formula for COPR. COPR equal to QL dot divided by W net in dot. So we already calculate the individual value of QL dot and also W net in dot. So just substitute into the COPR equation. So COPR value equal to 3.982. So from this value, actually, the value will tell you that for 1 unit of or 1 kilojoule, sorry, 1 kilowatt of electricity, so the refrigerator will absorb 3.982 kilowatt of energy from the refrigerator space. Okay, so that's the meaning of COPR. Okay, now let's say the question asks you to draw the complete TS diagram. So based on the value and also the phase that you already determined when you calculate the value of enthalpy from state number 1 to state number 4. So now you can draw the exact TS diagram. So where you will have a 4 constant pressure line, and state number 1 inter of pressure is 0.14 megapascal, and now we know that state number 1 is superheated vapor region. So you need to draw the exact point for state number 1 in superheated vapor region. So draw vertical line to obtain the point of state 2s on the constant pressure line of 0.8 megapascal. And also we have state 2a on the same constant pressure line of 0.8 megapascal. State number 3, the pressure is 0.72 megapascal, so you need to draw the point number 3 on the constant pressure line of 0.72 megapascal, and you know that the phase is subcooled liquid, so you need to put point 3 in the subcooled liquid region. And the last point is point number 4 in saturated mixture region, and the point will be on the constant pressure line of 0.15 megapascal. Okay, then connect all the points, so you will get the the cycle for the actual vapor compression refrigeration cycle for the example of 5.2. So this is how you answer the question involved with the actual vapor compression refrigeration cycle, and also how to draw the actual refrigeration cycle for the how to draw the TS diagram for the actual refrigeration cycle in this problem. Okay, so we have QH, W in also QL.